Howdy, everyone. Welcome to another week. How are we doing? Did we enjoy our snow day? Yes. Okay. That was really nice. I slept till like 10:30. So no class, there's no class Monday. So we're just jumping back in from like Friday and Wednesday or today's lecture. I don't really have any announcements in terms of administrative stuff other than you have a quiz next week. I think that's correct. And then believe it or not, your first test is like 2.5 weeks away. So that's kind of scary. But other than that, I'm here to answer your questions. Are there any questions for me about class in general? Okay. And then anything that you want to see today? It's all up to you.
Where to start? Where to start? I think I need like a rundown of like reviewing what lattice energy is. Like she gave us like all these equations today and I just don't understand it.
Okay, so let's do that.
Built H hydro with the ions, like stuff like that.
Yep. Okay, so let's kind of just break down today's lecture a little bit more together. And then we can talk about it there and everything. Right, so what we were learning, right, is all about solutions. So when we talk about solutions, what are the two parts of a solution? Good, we have the solute and solvent, which then gets dissolved. This is what's going to get dissolved. Right, and then the solvent does the dissolving. Right, so when we talk about lattice energy, this is going to be your solute dissolving in your solvent. What happens in that case? Right, you make solutions probably every day, right? A lot of them is salt water, pasta water, something like that. You add creamer to your coffee, that's a solution there. Right, so these are everywhere, but we can talk about the energy that goes along with them. If you're using hand warmers, right, that's kind of a solution. It's a little different, but the act of like that heat transfer is something that we're going to be talking about with solutions. Right, so we said that definition we said in class was solvation. Does anyone remember what solvation is? What does this mean? Yeah, perfect, right? So, right, definition is a solute particle is surrounded by solvent particles. But what this means is that, right, your solute getting dissolved by solvent. Okay. What does that mean? When we have, let's say, salt water, right? We have sodium and we have chloride. When we break up sodium and chloride, what does that break up into? That breaks up into two ions. What are those two ions? Na plus and Cl minus. Perfect, right? So we have these two ions that each have a negative charge, or sorry, they each have a charge, one negative, one positive. When we're saying that salt is dissolved in water, right, our solute is our salt and water is our solvent. Okay, so we have these sodium ions and these chloride ions being added to a whole bunch of water molecules. When we look at a water molecule, is that a polar molecule? Yes, where are our polar ends? Which one's positive, which one's negative? Perfect, right? So those have partial positives. And that means that our oxygen will have partial negatives. Everyone knows why oxygen is more negative than hydrogen, yes? Okay. Right, so oxygen is going to be more negative, the hydrogen is going to be more positive. When we combine our sodium positive ion, our chlorine minus ion, and then our water molecules, what is this positive sodium ion going to be attracted to? The negative of what? The negative of the water, right? We're no longer associating sodium and chloride together. They now have this barrier of the water interacting with them and getting in between. So what that actually looks like is that this sodium plus ion is going to be surrounded by a whole bunch of water molecules. Right? And they would make a circle. I'm going to do it kind of rough, right? But it creates this circle or this barrier around that sodium plus charge that we have. Right? And that's because opposites attract. That positive charge is going to be attracted to that negative partial charge of the oxygen. And in the same sense, that means that the chlorine minus ion is going to be surrounded by the positives of the hydrogen. Right, so it creates this barrier around them. So that's what solvation is, right? We're just dissolving our ion, or we're dissolving our particle in our solution. And we're creating these barriers around it. This happens, right? Very close together. These are very small. And so there's going to be atoms in between all of them. But if we're just looking at the sodium and chloride, that's what it's going to look like. So does that make sense what solvation is visually? Yep. Okay. One thing to note out, right? Solvation and hydration. These are going to be interchangeable when you talk about an aqueous solution. So if you say something is being hydrated, you're doing what we're doing right here in red, right? We're creating an aqueous solution. We're dissolving a solute in a solvent. They're the same thing when water. Yep. When you're talking about water, if it's something else, if it's a non-polar substance, then it would just be solvation. But when we specifically talk about water, then it's hydration. So this is aqueous solutions. Right, if something was being dissolved in methanol, right, then that would be just solvation. So what does this entail? What does it take in order to create this solvation or this dissolving effect? So when we take sodium chloride and we break it up into Na plus and Cl minus, what are we doing? Are we breaking or forming a bond? We're breaking a bond. What does that require energy, or does that release energy? That requires energy, right? All bond breakage is going to require energy. And if you think about trying to like break a board in between your hands, right? If you have to put an effort in order to break that board. So you have to put an effort in order to break that bond that's between the sodium and the chloride ion. So breaking bonds requires energy. Okay. So this means that the delta H of the solute is going to be equal to the delta H of the lattice, right? That's going to be the same. But what does that mean for delta H? Is that positive or negative? It is positive, right? This will always be positive.
Is that every scenario?
So whenever the delta H lattice is always going to be greater than 0 because we always have to break a bond in order to create a dissolving or a solvation effect. Okay. And when we talk about this, when we talk about the lattice, this is for ionic substances. Ionic compounds are the ones that create lattices. And so that will always break apart into its two ions or into its ions. I'm not going to say two ions, might be more. But it'll always break apart into its ions. And so since those have to break apart, that will always require energy to do so. Yep.
I'm sorry, what does that mean? The change in sign and the change in mass? Like.
So that's the change, they're saying the energy. So if we're looking at like just a regular, right, we say mx solid, and this goes to m plus and x minus, or I guess it would be. This process in this direction, right, in order for a chemical reaction to happen, requires a delta H. We'll always have a delta H. So this delta H change in energy is positive. You have to put in energy at the start of your reaction in order to break those apart.
So does that equation, maybe that question, like that represents like breaking bonds? So that equation is like the lattice energy.
That's the lattice energy. Yep.
Okay.
So this reaction here in its simplest form, right? We don't have an M element. There's just random elements, or random metals and non-metals. This is your delta H
Which is why it's positive.
of lattice. Yep. So you must put in energy to break an ionic compound. Say that again. Yes, right. So this is an endothermic reaction if we're looking at it from left to right. If we were to look at it, right, which is if we were to look at it going this way, now we're forming a bond. What does that do for delta H? It's negative, right? So what do we say? It doesn't absorb, it releases. Yep, gives off energy. So this would be delta H is negative.
That's because you're making bond.
And that's because you're making a bond.
So making bond is like
Is negative. Yep. Right. And so if you think about it, we are looking at, if we're looking at MX, right, that is a very stable compound. They're very happy. If we look at sodium, it's now given up its electron. It's sitting stable. It has a complete octet. Chlorine is sitting stable. It's gained its electron. It has a complete octet. They're very relaxed. We've now put energy into that sodium chloride compound, right? So it's like you riled up a dog and you gave it the zoomies. So now it's in the zoomies. It's now broken apart, right? We've released it. They now each have a either incomplete octet, right? We're missing one, or we have an extra energy level, right? So we're at this high energy level now. Once we take those high energies and they calm down, we're now relaxed. We've released energy, right? If a dog gets out of zoomies, it's released energy. So now we go back to that stable compound. So anytime you're breaking a bond, that requires energy. Anytime you're releasing a bond, that releases energy. Right, because you're sitting in a more stable state. Does that make sense? All right, so now we created a spot where we have two charges. But the other half of this is that the hydration, right, or the actual dissolving of this is always exothermic. And this is because once it settles as, I'm just going to draw this again. Once it settles as your hydration, where we have the water molecules surrounding the sodium and the chloride ions, this ion dipole interactions between the two are very strong. Right, we've now created a like mini bond, I guess we'll call it, right? Because we have a positive and a negative force being attracted to each other. So now it's no longer just a positive ion, it's a positive ion calmed down by the negative charges of the water. It's that negative ion calmed down by the positive charges in the water. Right, so those interactions there are very, very strong. That releases energy once they surround the atom. Once they surround the ion. So if we have a process that's going to increase our delta H, but then a process that decreases our delta H, we can combine those together and we can say that the delta H of a solution is equal to the delta H of, what did we just call it? Lattice, plus the delta H of hydration of ion. Right, so this is your bond breaking. And this is your bond forming. Any questions on that equation? So what makes delta H of solution negative? Yes, right? So when the delta H of hydration of the ion is releasing more energy than it's required to break that ion in the first place, we now have a negative delta H of solution, right? So when dissolving the ion releases more energy than required to break the ion, delta H solution is negative. Questions there? Okay, so what goes into the hydration of an ion? Does anyone know what goes into that? Right, we're looking at the charged particles and them dissolving. So if we have fluorine minus and chlorine minus, which one is going to have a more negative delta H of solution? Why? More electronegative, what else is it? If we're going to look at the periodic table, right, we have fluorine and then chlorine, bromine and iodine. What do we know about atomic radius as we go across or down the periodic table? It gets bigger, right? So if we're looking at fluorine and chlorine, why is fluorine going to have the more negative delta H? More negative. Yep, perfect. Right. So we'll have a more negative delta H. Because it's smaller, right? If we were to look at O2 minus and fluorine minus, which one's going to have the more negative delta H in this case?
Is having like this, what you just said about the having more of a negative delta, it's just same thing as having like very less energy, is that two different things?
So we're looking at the hydration of the ion here, and not necessarily the lattice.
It's like in my brain, I'm like applying like the same rules of like the greater charge and like the smaller.
Yep.
Right.
It applies to both, but what I'm asking for is applying to the hydration portion of it. Yep. Because if you have smaller atoms, they can be closer together, so it's going to require more energy to break that bond.
Like the same rules apply when you're trying to find out.
Yes. Yep. Yep. Because what I'm asking for is because we have this equation of Coulomb's law. For these are your charges, and this is your radius, ionic radius. So if we have a larger numerator, what happens to our force? Does that go up or go down? That goes up, right? So larger numerator equals larger force. So the more charge we have, the greater our force of attraction between them, right? Because the more charge that's going to be what's on top. And then what about R? Do we want a small r or a big R to make a big force? You want a small r, right? So then the smaller radius equals a larger force. So the smaller and more charged the ion, the greater the hydration of solution. Right, and this is because you have more atoms that can fit around that circle, right? The bigger it is, that means you have to spread them out around it. But now you can get closer together, your atoms can get closer together, and you can have more attraction between the solute and the solvent. And it all boils down to Coulomb's law in terms of charge and radius. Questions here? Right, and it does play into the lattice, right? Because you have two charges that are going to be competing with each other. So the bigger the atom, and then the more charged it is, or I'm sorry, the smaller the atom, the more charged it is, the greater that lattice energy between them, the greater that energy that you have to put into breaking them that is required. Any other questions? Does that clear up a little bit of like that equation we talked about today? Yep. So you would have to get that from the periodic table. So. You'll always be given a periodic table on your exams. And right, when we look at the periodic table, right, this first row here is always going to create positive one charges, right? And then +2, and then right over here, -1, -2. So as long as you know where that is on the periodic table and can find the charges that way, that's how you would determine what charge goes into that. They would tell you an element, yep, or a compound. Right, if you were given sodium chloride, then you would say, okay, sodium is +1, chloride's -1, that's a +1 and a -1 at the top. Yep, you can multiply them. Yep. You wouldn't necessarily ever have to solve for the actual force. It's just more going to be comparing questions, like which one's going to have the larger lattice energy or which one's going to require more energy that way. For the actual delta H, you would be given that.
Formula, like you're not solving for anything. It's more
More conceptual, more which one's going to have the higher delta H. So then which one's going to require more energy? What is that going to mean for my solution as well?
So just the world to find the delta H, which one is this? More. What would you say, like more positive? You use that. The purple rating.
Yep. Yes. Yep.
And what's the term like to find, not to like make it more positive, like which one is a higher delta H? What?
I struggle with this as well. I say a more negative delta H, a more exothermic. Yep. So I say a greater lattice energy or more positive lattice energy. Which one requires more energy, and then which one would release more energy or has a more negative delta H. Yeah. Quizzes will have some free response questions. Your exams will most likely be multiple choice.
H and like noise says.
Yes, the delta H of hydration and the lattice energy are opposites. A little bit more goes into the hydration, which is why it's not 0.
Lattice energy is positive. It's like negative.
Mhm.
It's breaking bonds.
One is forming bonds. Yep.
Why can't lattice energy be negative?
Because you always have to, lattice energy is talking about breaking apart that ion. So you can never have a positive delta H when you come to breaking an ion. That will always require energy and therefore always be positive.
And then hydration is negative.
Mhm.
Because we're making.
Yep, which always releases energy. Yep.
If hydration is, I thought hydration would break it apart, and then one would come.
So the lattice energy is what's breaking it apart. Hydration is the solid vent molecules coming around to surround it and making those pockets of dissolved particles.
Okay.
It's right, you have to break everything apart first before you can dissolve it. So it's the energy to break that ion and then the energy to dissolve that ion. Right, you can kind of think about it in 2 steps, where if you have a cup of salt and then you have a cup of water, they technically need to break apart into sodium and chloride ions, and then they get dissolved once they get into the water.
And what type of forces attract the ions and
That's gonna be ion dipole because you have ion charges from your sodium and your chlorine. But then your water has a dipole moment. That's gonna be ion dipole. Yep. You're looking at the strongest intermolecular force between the two of them. Okay. Anything else with solvation hydration? Does that clear up a little bit from what we did today? Okay, the next thing we can talk about is entropy. Does someone tell me what entropy is? This is disorder, right? I remember my AP Chem teacher in high school always said, now you can go home to your parents and next time they tell you to clean your room, that you could say that you're contributing to the entropy of the universe. I like to think I contribute to the entropy of the universe on a daily basis. Right? Create more disorder. Entropy is always increasing as the universe. When you are making things a solution, so solutions are going to increase entropy. Right, because we're no longer having just a compound, we have two things now. We have two ions. If we go from 1 to 2, that's increasing entropy, that's increasing disorder. Is an increase in entropy favorable or unfavorable? It's favorable, yep. So increasing entropy is favorable. It's preferred. Disorder is preferred in the world. So this is good for making solutions because we're always increasing entropy. And if we remember maybe a little bit of like the delta G equation, does anyone remember delta G? This equation. Does that ring a bell for anyone? Right. This being positive creates a more negative second half of that equation, which will contribute to delta G being negative. So increasing entropy is favorable. Right, so this means that your delta S, because entropy is delta S, will be increasing or greater than 0 for your system. Whenever you're creating a solution, you're always going to be increasing entropy. Your entropy gets higher. Yep. Yeah, I'll try to emphasize that. Your enthalpy is delta H, your entropy is delta S.
It's where it's not.
I don't think so. I think your delta S is always increasing. Because you're always breaking things apart. So you're always creating more disorder with it. It's just the magnitude of disorder that happens. So that's good there, I think. In a case where, right, going back to delta G, you can have times where your delta S doesn't increase enough, therefore making delta G positive, right? If delta H is positive and you have delta H, or you have a delta S that's a small positive, And then delta G is positive. This means that no solution forms. So this is like in oil and water, right? You're not going to have a homogeneous solution between oil and water because there's not enough entropy between the two in order to overcome the enthalpy that's required. And so that's why it doesn't mix. No solution formed. You just get oil on top, water on the bottom. Yes. Yep.
And then delta H would just stay a large positive and then solution one form.
Yep. Stay a large positive or, yeah. So in this case, if delta H is a large positive, you need a larger delta, positive delta S. You would like for delta H to be negative, and then that's negative, and then delta S is positive, and it'll always be negative.
Okay, so just delta S needs to be bigger. than
Big,
delta H
yep.
first.
Yes, yep. If they both favor formation, you'll always get a solution. Any other questions on that part? Okay. What other equations did we talk about today? Yes, yep.
Isn't that usually needed?
It's usually negative. Sometimes, right, there can be cases where it's positive. And in that case, right, then your delta S needs to be bigger than your delta H. And so that's that case there. But most of the time it's negative, so you don't need to worry about that. Yep. Okay. Yeah, we feel okay about like saturated and unsaturated solutions. We know what that means. Okay. All right. So then when the other equation we looked at today was Henry's law. Does anyone remember what Henry's law is? Yep. Yep, perfect. So what is S? And so entropy will always be delta S. Yep. So this is in units of mole over liter, which is also concentration. Right, so sometimes you'll see Henry's law as C is equal to KH over P. Excuse me, because you have concentration of something, but it is also solubility. Right, and solubility is just how much something can be dissolved in something else. But it is in moles per liter, which is a concentration unit, so you do need to have some sort of gram mass component, right? Substance component in a volume. Your KH is a constant. Right, if you need it, you'll either be given it to you, or you can solve for it, right? If you're given the concentration and the pressure of something else. And then P, we said, was pressure. And this is going to be in ATM. And then the constant is usually in molarity divided by ATM.
As well, like constants.
Yeah, usually the constants are given. It'll be given to you on your formula sheet. So you get like your periodic table, and then you get a formula sheet, and it's usually formulas on one side and then like any other charts or something that you need on the other side. She tends to break it up in boxes, so it'll just be in one of those boxes there. Yep. Okay. So this is the pressure. If you're solving for the concentration of a specific gas in a solution, this could also be the partial pressure of the gas. Right, you can solve for that. If you know the moles of the partial pressure, or if you know the moles of that gas in solution, you can solve for the partial pressure of that gas. So if we're looking at S is equal to KH times P, what is our relationship between solubility and pressure? If pressure goes up, what happens to S? It also increases, right? So these have a direct relationship. So increase in pressure increases solubility. So has anyone flown on an airplane? Yeah. Does anyone get a soda on an airplane? Do we have more or less bubbles in our soda? We have less. And why is that? Right? Pressure increases or decreases as we go up.
Less air above you, so like the pressure is.
Yeah, right. So
That's
right,
all
is
I
it, yeah. So the pressure is less up, right? Atmospheric pressure, if you're farther away from sea level, right? You have a little bit less pressure. So you have less bubbles being dissolved into your soda. So it's a little bit more flat as you get up. Whereas if you were to go like underneath the ground, closer to sea level, then you're gonna have more bubbles. So the increase in pressure increases the amount of bubbles in something. So more pressure equals more gas particles dissolved. That's also right. If you leave something out, that goes flat because the pressure is different. Pressure is less than in a compressed can. Okay, let's do an example of this. So we'll say so this says N2 has a partial pressure of 330 millimeters of mercury at 25 degrees Celsius. What is the solubility of nitrogen gas in water if the KH of N2 is 2.4 times 10 to the negative 3? Okay, how are we going to solve this one? Perfect. So we need to convert the pressure. So we have 330 millimeters of mercury. Does anyone know what that conversion is? That'll be given to you if needed. Sometimes you use a conversion so much it sticks. So we have 0.4342 ATM. How are we gonna solve for the solubility? Perfect, right? So we're just gonna use our equation. We have solubility is KH times pressure. So we have 2.4 times 10 to negative 3 molarity over ATM times 0.4342. I got solubility is 1.04 times 10 to negative 3 molar. What if I wanted this in grams per liter? Right? So we know that M is also moles over liter. So if I wanted it in grams per liter, I need 1.04 times 10 to negative 3 moles over liter. I'm going to use the molar mass of that nitrogen. So 1 mole of N2 is, does anyone know hydrogen or nitrogen? 14.01 grams per mole. So what's our molar mass of N2? 28.02 grams. And then I got 2.92 times 10 to the negative 2 grams per liter. Alrighty, any questions there? Yep.
So solubility and molarity the same thing?
Yeah, it's a concentration unit. So it's just looking at, right, solubility is how much can be dissolved and concentration is how much is dissolved. So you're just looking at the difference there. It's the same units of moles per liter. Okay. I heard a couple discussions about the clicker question. Do you want to do that one together? Try to talk about it? Okay. Do you just want to do the same one from class, or do you want me to give you a slightly different one? Okay, we'll do the first one. We'll do this one and then I'll find another one. So All right, so where are we gonna start off with? Right, we said if 27 grams of acetylene dissolves in 2 liters of acetone at a pressure of 12.7 atm, what is the Henry's law constant Kh of acetylene in molars per atmosphere? Kind of, right? So if we know the equation we're looking at, what is the equation? Perfect, right? We have S is equal to Kh times pressure. What are we solving for this time? We're solving for Kh. So in order to do that, we would say that Kh is equal to solubility over pressure. Okay. How does that help us? What do we do from here? Right, so we need to figure out our concentration. What are we given that can help us get to our concentration? Right, we're given the molar mass of this. Right, we know that solubility has to be in moles per liter. Are we in moles yet? No, how can we get there? By the grams by the molar mass, right? So we'll have 27.0 grams. 26.036 grams times 1 mole. So that's 1.037 moles. Are we in moles per liter yet? Nope. Can we get to moles per liter? How? Perfect, right? Here's our volume. So we can take 1.037 moles divided by 2 liters. So we get 0.518 molar. What is that? What letter does that satisfy? Moles over liter. That gets us our S. Do we have P? Yeah, that's given to us, right? We say we have a pressure of 12.7. So now we can say that Kh is 0.518 molar over 12.7 atm. And so I get 0.0408 molarity over atm. Does that make sense for the clicker question now? Right, so I'll point this out a lot, especially coming up in these next chapters with like ice tables and everything. Using your units to your advantage to create a roadmap is super, super important. So if you can see, okay, I have grams, I have to get to moles. I have a grams per moles. That's kind of my conversion factor there, right? I can use that. And then I know that I need to get to moles over liters. I'm given my liters, that satisfies that one. I'm able to, get to moles. I have my liters, I can get to molarity. How does that get me there, right? If you can use that as a roadmap, that's super, super helpful. Sometimes you might not even know what to do, but you need to convert units, right? So if you can convert your units, sometimes that puts you in the correct direction. I think I remember taking a physics class or doing one physics question and I got the right answer just because I followed my units. So take that with as you will. But units are super important. I highly recommend writing them down, especially in the beginning stages of learning something. Any other questions on Henry's law? Okay. Okay, I'll give you one question. You can either do it here or you can take it with you on the road. Yep, thank you. Have a great day. Yeah, thank you. Thanks for coming. They should be posted already. Yes, yep. I can double check that for you right now just to make sure. I know I thought I did it yesterday, but let me just make sure it attached. Sometimes I save things before they're done. Were you able to find that on the office hours page? Okay. Yeah, I think they should be there. Yeah, they're there. Yep, of course.
Okay, so I just want to like make sure like understanding the right concept.
Mhm.
So with like, so overall, will always be positive,
Mhm.
and hydration will always be negative.
Yes.
And then lattice energy is like the breaking of bonds
Mhm.
and ions.
Yep.
Okay, and then lattice energy, or not lattice energy, hydration is like the making of bonds in water.
Yes.
Okay, and, okay, so then, gotcha. And delta H, that's like just enthalpy,
Mhm.
but what does that necessarily mean?
That's the heat of the reaction, right? So that's the energy required or released for a reaction.
Okay. So whenever we're making the bonds, we're releasing energy
Yes.
for hydration?
Yes.
Okay, so because like for lattice energy, we're having to, it's like we're using energy, because like you have to use energy to break bond.
Mhm.
So like you'd be absorbing energy.
Absolutely.
Okay, and then hydration is releasing.
Yep.
Is releasing.
Yes. Yep. And so overall, you can combine those two and you get the delta H of solution, and that's the combination of the both of those.
So for like a question on like, question in general.
Mhm.
Would that be like given to us in like a problem?
Mhm.
Like it would give us like the lattice energy or like the delta H of the hydration, we would add them together to find the solution?
Yes.
Or
Yep.
like get one and off the other?
Yes. Yep.
Okay, gotcha. And then like this like mx and then m plus the lattice energy equation.
Yep.
Is that just like conceptual, just trying to understand, it's like the breaking of ions?
Yes, that's just what it's doing. You can put in any non-metal for M any metal for M and any non-metal for X, right? And it will do that same thing. So you could do magnesium, it's gonna end up as a 2+.
Will it always require positive and a negative?
Yes, yep, because it's always gonna be an ionic substance, and that's always gonna be positive and negative. Mhm. Does that help?
No, that really does help.
Okay.
A lot. So the only way that like entropy, like delta S and delta H, are they related in like just the way of like you want delta S to be greater than delta H for the solution form? Is that really it?
Yep, then it all comes back to that delta G equation.
Okay.
But as long as entropy is increasing and delta H is negative, the solution will always form.
But if it's like opposite, then it's not.
Then no solution forms. Yep.
Okay. Thank you so much for your help.
Mhm.
It's also table for delta P, I remember like one.
Yep.
It's like the positive, one is positive, the other.
Yep.
Would that be helpful?
If you just review that, just like, oh yeah, okay, that makes sense, and see how it plugs into the equation.
Yeah.
That's really all the refresher you need. You'll do plenty of delta G later on in the semester too, and that'll all be a refresher again as well. But that equation or that table is super important. Once you see delta G broken down into delta H and delta S and can understand those, that like I think is a really good turning point for
So
understanding
for
chemistry.
hydration, like it's like, an ionic compound being dissolved in water.
Yes, yep,
mainly. Okay.
Yep.
And the opposite of that, we called it, you said it like was used interchangeably with hydration.
solution, yep, so that's just if you're dissolving anything in any substance,
Okay.
that's solution. When you're dissolving ionic compounds in water, that's hydration. Right, so it's like umbrella term of solution, and then, or what do I always call it? Solvation, umbrella term of solvation, hydration is a subset of solvation. right? All hydrations are solvations, not all solvations are hydrations.
That makes sense. That makes so much sense. Thank you so much for
Yeah.
your help.
Absolutely, anytime. Mhm.
Yeah, it's like just from the warm mass, right? But it asks to like get stuff from Alex, and I think I'm not sure.
Okay, let me pull my Alex up myself and I
Alright.
can, it's question 11.
Yeah, it's question 11 for the properties of solutions. You only host these weekly?
I host these weekly and
Okay.
then before exams, I'll do a longer session
Oh,
of this.
yeah.
And then I will do a Zoom review session like the night before.
Do you know what's the difference between these sessions and the SI sessions?
The SI sessions, right, so like I'm a grad student
Uh-huh.
and then they're undergrads,
Uh-huh.
so they took the class more recently than y'all.
Okay.
So like just in terms of people, that's different. And then I think they go in with a little bit more prepared questions. So, right, obviously I could do a couple questions with
Yeah.
y'all, but it's more like do these,
Conceptual and
yeah,
stuff,
and
yeah.
stuff. I love doing practice problems, so I
Yeah.
think for this one, it's a little bit easier to just break it down and talk about it for a
Uh-huh.
little bit. But later on the semester, like we'll do a whole bunch of ice tables and stuff together. So I tailor it more towards you. I think they have set plans when they walk in.
Oh, alright.
I like prepare for everything, right? And then
Yeah.
pick what y'all want to do.
All right, that
Yeah.
makes sense. Yeah, just
Um,
question 11.
When was it? Okay, so. Yes, so do you know what this concept is?
It's the, like, I know you have to take difference in the temperatures.
Mhm.
Between like the normal one and the freezing here,
Mm-hmm.
and I'm not exactly sure actually.
Yep,
It might
so-
be the concept. Yeah.
Yep, so I don't think y'all have touched about it yet, because I was looking through her slides
Oh,
today.
that's why it's due way later.
Yep,
Okay.
because you will talk about colligative properties.
Oh, this is part of colligative properties?
Yep, you'll talk about that on Monday or Friday,
Mhm.
Friday.
I can review it before. I just didn't know what it
Yeah,
was.
it's a colligative property. Right, so what they're saying here is, right, a mass of something is dissolved in something else. So right, you need the molality.
Okay.
So that's why you need the molar mass of compound X, and then it's dissolved in the grams of cyclohexane. That's your solvent. You can get the kilograms for that. Right, so
That's all right. I just didn't even know where to begin.
Yep.
Because I was like, what is this? What concept is this?
there's something else, I think. I think it's delta T, that, something like that. If you look up colligative properties, then it'll tell you. But you need, I know you need the molality and then whatever. You have the desired delta,
You
the
probably
change
have
in
to switch around
temperature.
things,
Yep,
yeah.
you just need to switch around a couple of things, and then I think you need a constant for the cyclohexane, because the cyclohexane will have, right, that has like a Henry's law constant, right? It
Oh,
has a
okay.
constant for how much the temperature is going to change. So it's like its resistance. It's like its specific heat and then its resistance to change.
Okay, okay,
But
okay.
it's another
Oh,
thing that would be
analogy
given
makes
to you.
sense.
So that's
Okay.
what's needed from the data resource.
So do we have like, oh, so you need the like the usual freezing temperature and the Henry's law constant for this compound.
So this one, you don't need the usual freezing because it gives you
It gives you the freezing at,
solution is measured. So you'll probably need the original freezing
yeah,
point.
that's what I was
Yeah,
looking
because then
at.
you can find delta T and everything. Yep.
Yeah, yeah,
Yep.
okay. Thank you so much.
Yeah, no problem.
Is this one?
Yeah, no problem.
So it seems like sodium and they close it around.
Okay.
How would I know?
I don't think you necessarily need to know that. Like the actual number of water molecules. You just need to know that it's gonna be different. If we look at the sodium plus molecule and the chlorine minus molecule, which one's smaller? Right, and do you know why it's smaller? Yes, but even if we didn't know how many molecules were around it right now, do we know why it's small? So if we look at sodium, we have originally 11 protons. If we have a sodium plus ion, how many protons do, or, and we have, if we have sodium plus, how many protons do we have? 10. How many electrons do we have? I'm sorry. We have 11. How many electrons do we have? This one's 10. So now in our nucleus, right, we have 11 positive charges, but on the outside, we only have 10 negative charges. So if you think about a buddy system, right, there's going to be one proton that doesn't have a buddy. So now it can buddy up with every single one of them, right? So it's going to pull its electrons in a little bit closer to the nucleus, so it gets a little bit smaller. If we look at chlorine minus, this one has 17 protons, and now it has 18 electrons. So now the electrons have one lone guy, right? They can't buddy up. They have one extra electron that's going to spread it out a little bit more, right? So we have sodium here, and then we have chlorine minus here, right? So they're a little bit different in size. So now only 4 can fit around this one. 6 can not fit around this one because it's smaller in nature. Yep. Does that help?
Yeah.
Okay. Howdy.